Hey there, and welcome. Today, we are going to tackle quantitative chemistry. And I know, that probably sounds super intimidating, but I want you to think about it in a totally different way, like we're building an awesome toolkit. Seriously, these are the core skills that let chemists measure, predict, and really understand the world on a molecular level. So, let's get building. It really all boils down to one simple but kind of profound question. How in the world do you count something you can't even see? It's not like we can just line up a bunch of atoms or molecules on a desk and count them. And yet, this is the exact problem that chemists have to solve every single day to make, well, everything, from medicine to new materials. So here's our game plan for today. We're going to start with the absolute bedrock, precision and measurement. Then we'll get into the chemist's secret weapon for counting, the mole. After that, we'll learn how to decode chemical formulas, figure out the recipes for reactions, get a handle on solutions, and finally, learn how to judge our results like a pro. Think of it as a step-by-step guide to building your chemistry expertise from the ground up. All right, first things first, we have to lay the foundation. Every discovery, every experiment, and every single calculation in chemistry depends on one thing: getting good, solid, reliable data. And that all starts with how we measure things. And, this image just nails it. Take a look at the three different rulers all measuring the same door. The ruler at the top, it can only really tell us the door is about 0.8 meters wide. But look down at the bottom ruler, it has so much more detail we can say with a ton of confidence that it's 0.772 meters. So the takeaway is simple. A better tool gives us a better, more precise measurement. This brings us to a really crucial concept: significant figures, or as you'll hear all the time, sig figs. To put it simply, they're the digits in a number that actually mean something. That jump we saw from 0.8 to 0.772, that's all about having more sig figs. They're like a code that scientists use to tell each other exactly how precise their measurement is. More sig figs means more trust in that number. Okay, so the rules for counting them, they're actually pretty simple. Any digit that's not a zero, it always counts. Zeros that are sandwiched in the middle, yep, they count too. Zeros at the very beginning, nope, they're just placeholders, so they don't count. And the tricky ones, zeros at the end, they only count if there's a decimal point somewhere in the number. This table right here is a perfect cheat sheet to keep handy when you're studying this stuff. And this all leads to the absolute golden rule of calculations in chemistry. When you start multiplying or dividing, your final answer can't just magically become more precise than your least precise measurement. You always have to round your answer to match the smallest number of sig figs you started with. All right, time for the next tool in our kit. We're about to talk about the mole. And I'm not kidding. This is maybe the most important concept in all of chemistry. Just think of it as the ultimate bridge that connects the tiny, invisible world of atoms with the stuff we can actually see and weigh in a lab. So what even is a mole? Don't overthink it. A mole is just a word for a certain quantity. Just like a dozen always means 12 of something, a mole always means a specific, just much bigger number of something. It's the concept that lets us count atoms just by weighing them. It's that simple. And this is the magic number. It's called Avogadro's number. 1 mole of anything, whether it's atoms of carbon, molecules of water, or even donuts, contains this many of them. It is an absolutely mind-bendingly huge number, which, is exactly what you need when you're trying to count something as ridiculously tiny as an atom. Okay, so how do we actually use this thing? Well, the process is actually surprisingly easy, as you can see here. First, you just find the mass of 1 mole of whatever you're working with from the periodic table. That's its relative formula mass. Then you just use this simple formula. Divide the mass you measured by that molar mass, and boom, you've just figured out how many moles you have. Okay, so now we can count using moles. Let's add another tool to our collection: decoding chemical formulas. This is how chemists can take some experimental data, maybe just some percentages of elements, and work backwards to figure out the exact chemical makeup of a mystery substance. First up, you've got to get the difference between two kinds of formulas. The empirical formula is just the simplest possible ratio. So, for example, a molecule of C2H4 can be simplified down to a ratio of CH2. But the molecular formula, C2H4, tells you what the molecule actually is. Think of the empirical formula as your first clue, but the molecular formula is the final answer you're looking for. So how do we find that final answer? Well, it's kind of like a little logic puzzle. Once you figured out the empirical formula, you calculate its mass. Then you get the actual mass of the whole molecule from a different experiment, and you compare the two. In the example on the screen, the real molecule is 3 times heavier than the simple ratio. So what do? You just multiply everything in that empirical formula by 3, and you've got your true molecular formula.
All right, we can count particles, we can decode formulas. Now it's time to put it all into action with stoichiometry. Don't let the weird name scare you. This is basically the chemistry of recipes. It tells us exactly how much of each ingredient we need for a chemical reaction, and it lets us predict exactly how much product we can expect to make.
Now, here's the best part for when you're trying to learn this. The process is always the same. First, you have to have a balanced chemical equation. That's your recipe. Next, you take the mass of the thing you know and convert it into moles. Step 3 is the crucial one. You use the ratio from that balanced recipe to figure out the moles of the thing you want to know about. And finally, you just convert those moles back into a mass. That's it, every single time.
So far, we've mostly been talking about pure solids and gases, but let's be real, a ton of chemistry happens when things are dissolved in water. So our next set of tools, concentration and titrations, are all about understanding the chemistry that happens in solutions.
The key unit here is molarity, which we show with a big capital M. All it means is the number of moles of a substance that are dissolved in exactly 1 liter of a solution. It's the standard way chemists talk about how strong or concentrated a solution is. Basically, how crowded it is with stuff.
And making a solution with a really specific molarity is one of the most fundamental skills you learn in the lab. This slide shows you exactly how it's done. You start by weighing out the perfect mass of your solid. You add it to this special flask, it's called a volumetric flask, and dissolve it in a little bit of water. Then, and this is the important part, you very, very carefully add water right up to that little line etched on the neck. It's all about precision.
All right, we're on to the final tool for our kit, and it's all about judging your own work. You know, it's not enough to just do an experiment and get an answer. A real scientist has to be able to evaluate their own data and know just how good their results actually are.
So take a look at this data table. Let's pretend 3 different students all did the same experiment. You can see their results are all kind of close, but they're not exactly the same, right? Student A's results seem a little all over the place, while student B's attempts are all clustered super close together. So the big question is, whose data is better? Well, to answer that, we need to get a few key terms straight. First is accuracy, which is just how close you are to the real, true answer. Next is repeatable. This is about consistency. Can you do the experiment 3 times and get the same result over and over? And finally, there's reproducible, which means can someone else follow your instructions and get a similar result too? The absolute best scientific data has all 3. And finally, we've got percent yield. Now, I want you to think of this like the final grade you get on your experiment. You used all that stoichiometry stuff to calculate the theoretical maximum amount of product you could possibly make in a perfect world. Then you weigh what you actually made in the lab and compare the two. A higher percent yield means a more efficient, more successful reaction. Simple as that. And there you have it. We've built the whole toolkit, from mastering significant figures and counting with moles, to decoding formulas, writing reaction recipes, and analyzing our results. These aren't just a bunch of random topics from a textbook. They are the real practical tools that let us ask and answer meaningful questions about the world all around us. So, now that you have the toolkit, what problems are you going to solve?